So thank you very much for the invitation to come here. It's a pleasure to be here, and I'm quite excited about speaking to a transhumanist audience. First of all, because I'm a transhumanist myself, so it's always nice to share ideas, and also because I was actually looking at my past presentations, and the first invited talk I ever gave was in 2001, about 10 years ago, in the Transhumanist conference in Berlin. And I've actually looked into some of the predictions I made about the field of aging in that conference. And I'll mention a couple here. But I'll start with a broad overview of the field of aging, which is my field of study. So I work on biology and genetics of aging. Tell you a little bit what I do later. So I'll start with an overview of the field, the current state of the art, which is, I would say disappointingly, very similar to the same overview I gave 10 years ago. The slides are a bit nicer, I guess. Google Images didn't exist 10 years ago, so graphically it's nicer, my overview. But it's very similar to core concepts to what I did 10 years ago. And then I'll tell you about what the prospects are of actually curing aging, some ideas on how we can go on about this. I won't go into a huge amount of detail. I'll tell you about some of the projects in our labs and projects of other labs. I won't go into a great amount of detail because I know you're a broad audience with broad interest. Not everyone is an expert in biology and in genomics. But of course, if you have questions or if you want me to discuss in detail any particular point, please let me know. And so I'll start with my usual introduction to the field of aging. I've been doing it for 10 years. And I've used this quote 10 years ago in my talk as well. The reason I use this quote from almost that is because I like to remind people that they're going to die. Because we tend to forget about it. I think it's human instinct that we try not to think that one day we're going to die and the eternal oblivion. I mean, if you're a transhumanist group, I presume most of you are not that religious. I would assume maybe that's a few exceptions. But, and I think that the fact that we're going to die, and thinking about it is actually helpful for biomedical research. Because if we think about that, and we think about why we're going to die, and in modern society, most of it has to do with aging and age-related diseases, we will do a greater effort to try to fight the causes of that. And clearly, in modern societies, of course, like the UK, the major cause of that directly or indirectly is aging, and age-related diseases, cancer, heart disease, degenerative diseases, etc. So most of you will die of a age-related disease. And so from a transhumanist perspective, and from an individual perspective as well, if we are to do, to follow the dream, in terms of transhumanism, I would like to one day explore the stars. I would like to one day go to other planets. If we are to do that, then clearly aging is the first obstacle to transhumanism and to transhumanists. And so, ultimately, what I would like to do is to cure aging. In other words, to radically extend our lifespan. And I saw on your website that you had talks by Robert de Grey, so we share the same goal. The idea is I think he estimated that if we were to cure aging, I think our average lifespan would be about 5,000 years, which I think is a realistic prospect, if we cure aging, of course. But that's something I'll discuss a little while later. So I'll give you a quick overview of the field of aging. Aging is a nice field to work on because everyone knows what it is. Some idea what aging is. And, of course, aging also, at the functional level, with age, frailty will increase. I think Alex Comfort defined aging as an age-related process of loss of viability and increasing vulnerability. And you can tell the number of changes. There's obviously functional changes, there's obviously physiological changes, there's age-related diseases, that diseases incidence increase with age. A few exceptions, there are diseases decreasing with age, those are rare. And of course, even if you start looking at the details, so at the cell and molecular level, aging entails a number of changes. So we can characterize the aging phenotype, but unfortunately, we still don't really know why we age. We don't know what are the driving factors of aging. What are the cellular molecular mechanisms of aging?
I gotta get her.
So there's, I'm sure you've heard of a number of theories of aging, theoretical theory, DNA damage, theory of aging. I'm not going to cover them. But you know there's multiple theories of why we age. Unfortunately, we don't really know which one is right, which one are wrong. Medvedev, about 20 years ago, he cataloged over 300 different theories of aging. And they haven't actually changed all that much. There's the idea that some types of damage accumulate, like oxidative damage or DNA damage, hormonal changes. There's a number of theories. This is a network model from João Pedro, which I guess is also transhumanist and life extensionist, of the different types of cellular molecular changes that occur. Well, these are cellular changes, but there's also extracellular down, but included at the top of the picture. But the point is to show that there's a number of changes, a number of molecular changes with age. They may all interact. Some of them may be more important than others. In short, we still don't know. There is, however, some reason to be optimistic that we can intervene in the process of aging. I've always been fascinated by species that appear not to age. Finch called them species of negligible senescence. And this includes some complex vertebrates like turtles and fishes. What I mean by species that appear not to age is that they do not show the typical signs of aging observed in humans and I guess all other mammals, as far as we know, which is they don't exhibit an increase of mortality with age, which is fairly characteristic of aging in mammals. So, for example, in humans, after age 30, your chance of dying will double every 8 years. And in mice, the same occurs on much shorter time scales.